指指よいしょよいしょ女よお上手指指 Hi, how's your recess, guys? We're back at it again, aren't we? Aren't we? Yahoo! 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 Okay. What you guys eat? What did you guys do? I had meat. I had meat. Meat and rice. Really good. I love it. It gave me the mad shark syndrome though. I'm allowed to admit that. It's okay, I can say that because VTubers don't poop. Wait, what? What the fuck am I saying? Idols don't poop, but I'm not an idol. Yogurt with bread? That kind of sounds kind of good. Have you seen like shakshuka before? You know the thing with tomatoes and eggs and Greek yogurt? Ah. Ah. Yeah. I think what we're gonna do for now is move on to ketones. Ketones and aldehydes. I've like tried to rationalize this with myself. If I can get through this playlist, I will post something. But then if I don't get through this playlist, then that thing will never see the light of day. So you guys have to somehow it's like within reason, you know? Like you guys have to somehow manage to keep me accountable and get me through this playlist. There's technically 1, 2, 3, 4, 5 videos, including the one we're watching right now. Yeah. Sorry, Gouda. I think it would have been too easy just because I lost tic-tac-toe to post something. My anxiety is way stronger than that, bro. So alerted. I'm Max. Oh wait, I thought you died. Hi Kimchi. Never seen Usa go to the bathroom. Idol dream is just real. I literally just told you I went and took the fattest dump of my life. I emptied out my guts, bro. Hi. Nope, still alive, barely. Aw, sorry. I don't know if this will give you any additional energy or not, bro. Ocam is kind. Well, what's your thoughts on Ocam, guys? Do you like it? Can you hear me stalling? you told us you could be lying. True. Wait, you kind of got me there. I hate it. No. Ocam is literally the explanation for bio, though. The highest chem level I've taken was AP Chem in high school. Why did you take AP? Why did you take AP Chem if you're just gonna go into CS, man? That makes no sense. You just try hard, Kimchi. It was so funny. My AP Chem teacher, I think everyone cheated in their class, and then he, like on the day of the exam, he was like, you guys are all gonna get 5s, right? I just know it, and he was bragging to the principal that, like, what is it? That we were all gonna get 5s, and I think half of the class got like 2s and belows. Nami though, Nami. Didn't have to take lab in college because of it? Damn. Ipichem. Mama. Okay. That's enough stalling for me though. Now we get into it. 3 ketones and aldehydes. Delicious. Amazing. Do I have my CC on? Sorry if you guys hear crickets in the background. It's really hot in my room. I think I'm literally gonna die if I don't open my window. I might actually die.
Back Chapter 6 is aldehydes and ketones, which are formed by the oxidation of alcohols, which are formed by the oxidation of general compounds, right? So in organic chemistry, if you take a basic carbon,
Damn, I'm like
structure,
freezing here.
oxidize it,
It's
it
freaking
turns
like
into an alcohol,
80 something degrees in my room.
or a ketone. It might
It's an
turn into
oven in
gas,
here.
It might even turn into carbon dioxide. Right?
My
So
chocolate
it goes up
melted.
the oxidation ladder. And that's the way they actually structure these chapters as well. They go up the oxidation ladder. It's just that no one ever told you that. And now I'm holding your hand through it, right? So we talked a
No
little
AC.
bit about naming
Mama Usa's a bit of a
different
cheapskate.
ketones
She
and aldehydes, stuff
doesn't
like that.
let
When
us
it's
turn
not
on
the
the
highest priority,
AC.
it's not so. When it is the highest priority on a ketone, it's ONE, O-N-E, like butanone. And then in aldehyde, it's butanal, right? Cool. So the first thing is nucleophilic addition reactions to ketones and aldehydes. So I want to talk to you about hydrate formation. So if we have an aldehyde, acid aldehyde, and we put it in a solution of acidified water,
Yeah.
we can observe a protonation of the carbonyl oxygen
Oh.
that will swiftly be followed by attack of the labile carbonyl carbon.
Is that an SN1? Or no? Yeah, SN1.
When we hit the pothole.
Why did that fucking scare me, man? God damn. I was like, Geico. Have you got on your insurance, guys? Get your insurance. Geico saves you 10% or less or more or something on. What the fuck is this mixture? This accent makes no fucking sense. I don't even sound like the Geico lizard. God. Okay, we're back.
And in order for the
That's so real.
it is
I
more
was
than
blinking
likely,
out like that.
or just for the simplicity of the reaction, we write that this gets deprotonated by another one of these starting material in order to perform the first step of the next reaction, right? So we see the carbonyl carbon coming, grabbing that, and we get, when in reality, it's probably the solvent that's coming to do this. And it's going to make another H3O plus, and then that's going to protonate another thing like this, blah, 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 right? And then we get something known as a hydrate.
Oh, just kidding.
I will quite literally, let me make sure I'm naming this properly. I will give $5 to anyone who can tell me what type of molecule that is, other than a hydrate.
A tetrahedral one?
What type of diol?
Dial? Ester?
There's two types of diols. This is a specific one.
Geminal?
I can't give you any more hints than that. That's coming next.
Ceto?
That's reducing sugars. We'll talk about that in a second as well. This is called a geminal diol.
I fucking clip that! Clip that! Clip that! Tag me in that! What did I say? What did I say? That is a fucking geminal diol. Never doubt yourself, Usa. You are a fucking genius. Sorry. I need to give myself something. Sorry.
Diol, which is different than a vicinal diol.
Which is
A
on
vicinal diol looks like
opposite
this.
end, I think.
And it's what you create when you react a double bond with OSO4.
Oh.
Vicinal diol. That is a vicinal diol. How do you remember geminal and vicinal? I always thought that this little
Gemini.
two-spoke thing and the circles look like a gem, like little diamonds on top of spokes.
Oh, I thought I was thinking
Geminal.
Gemini
And
twins.
vicinal means they're just in the same vicinity of one another. They're not on
Ah.
top of one another. They're just in the same neighborhood, right?
Wait, can we talk about this reaction first? Okay, you have H3O plus. This is gonna act as your acid that's gonna give you that H. The video volume? Oh, is it? Comment. I think I turned it down because I was worried that it was blasting out your ears, but I can just turn up the desktop audio then. But yeah. H3O plus, this is gonna act as your acid, right? So then this O, the electron pair on the double bonded O from the carbon we were watching together. You wanna learn OChem too? That makes me so happy, man. You don't get it, bro. You literally don't get it. Whoa. Okay. This is going to this H and plucking it off and then returning it to this, right? And then this is getting tossed somewhere. And then essentially this is protonated now with that H. So then since you have that positive charge on this, then... Oh, you can't? What? Wait. This? Can you see it now? Was I on the wrong screen? Come in. Okay. Sorry. Thank you. Okay. So, this was what I was saying. This is H3O plus behind this beautiful man's beard. H3O plus. And this is going to be your acid, right? This electron pair on this carbon, or this carbonyl, or aldehyde, sorry, it's going to go and it's going to pluck off this H. It's going to bond with this H. And then that's going to cause this bond to break and go back to this. This is going to be water. This is going to go somewhere. It's going to go yeet off somewhere. So then what's going to happen is this is protonated, right? Protonated as in now it has a positive charge and there's a bond to an H. This O right here. And then what's going to happen is because this right here, this oxygen has this plus charge on it, it's going to make this electrophilic. That thing we were talking about where, what is it? It's electron poor so that it wants to get electrons, right? So that makes it easy for something like OH minus, which is nucleophilic, to come in and hit it. Come in and hit it from the back or whatever, right? Come in from the back. And then once it comes in from the back, it's going to take an electron from this bond here, kick it up, and then essentially you're going to get this structure right here where you have that that OH minus, and then you have that, or I think that's that, right? Or is this H2O? The NTR, it's kind of like the NTR substitution. I don't know necessarily. This sounds like last chapter. What changed? I think because last chapter we talked specifically about carboxylic acids. Those are the ones where, if you look at the where I'm circling right here, instead of this H, it has to be like an OH or something else. And those molecules can be found in between, like chains of carbons. But this is an aldehyde. It is a type of carbonyl compound, the little boner thing. It has to be at the end of a long chain of carbons. Always at the end. You can never find it in between something. It just can't. It's not possible for you to have this unless it's at the end of something. Yeah, that's the difference. I think. Yeah. But, is this H2O? Sorry, bro. Wait. I'm gonna move you back. Oh, okay. No wonder, I'm confused. So you have this water. That's why. You're gonna have this water. This electron pair from this water molecule, specifically on the O, the oxygen, it's gonna come in, hit it from the back, and then it's gonna push an electron pair from this bond to this positive OH. Right? Or, yeah. This positively charged oxygen molecule, and then that's just gonna turn into regular, like uncharged, but then you have this what is it? This positively charged H2 and then O bonded. And then you need to get rid of that. So then I guess he's saying some kind of solvent, any solvent. Maybe let's say this H2O is gonna come in and it's gonna rip off that H. Gonna rip off that H. Then you essentially make this little Gemini twin thingy right here. That's pretty cool, isn't it? That's pretty neat. Huh. Okay. So that's hydrate formation.
Geminal and vicinal. I always thought that this little two-spoke thing and the circles look like a gem, like little diamonds on top
Diamonds,
of spokes.
yeah.
Geminal. And vicinal means they're just in the same vicinity of one another. They're not on top of one another.
Aww.
They're just in the same neighborhood, right? Geminal and vicinal dials.
Vicinal dials.
Like the pinnacle rearrangement begins with a vicinal dial. So a vicinal diol, otherwise known as a hydrate. And this is an aldehyde hydrate.
Aldehyde hydrate.
There's an H right there. To make a ketone hydrate.
Ah, okay. This is for an aldehyde. Aldehyde because there's an H. Okay.
Same exact thing.
Okay. Hydrate. Hydrate.
If you don't wish to copy this down, you don't
If
have
it has
to,
an
'cause it's literally
An
the
H
same
is a
thing.
hydrate? No.
I'm doing it for the sake of
Hydrate
confusion.
is if you add OH, but the H is what determines whether or not it's an aldehyde or a ketone hydrate. Yeah. Same shit, I think. Kind of? Sort of? Yeah, you're still using H3O plus or H2O slash H2O. Kind of?
Geminal dial from
Then you
a
point to the H.
ketone
No,
to
it's
no
okay.
H over there.
I'm glad you asked.
Good.
I was also like confused too. Let's look at this. Oh, so if you make a ketone one, then it's just you replace it with a ketone. Oh, なるほど。なるほど。
I'll give you a second.
Okay. Excuse me.
I get tired out here sometimes.
Come back, King. Come back. Stay hydrated. Real.
Pretty. Our last day here. No, like when I leave you guys on your own, and you never see me again ever.
Why? Don't leave. No.
You
Don't
can
leave.
finally clap on that day, yeah.
There may be two
Oh no,
students
I'm coming
bugging
back
out.
next year, and the next year, and the year after that.
Bro is graduating.
Yeah. I'll see you guys another time, don't worry. I mean, I'll see you guys. I might see you, a couple of you guys at medical school. Who knows? I'm sure a couple of you will come to downstate. Here's hoping. What's the downstate MCAT average for my class? It's a 516.
What the fuck?
It's 516. We have 9 people who scored above a 520, and I'm one of them.
Wow.
In a class of 230, I think.
That's my old school. Tensai.
But
Tensai,
Downstate
tensai.
loves to take kids from Brooklyn. So, roll your dice and do well. Both.
It's gonna be 10.
Roll your dice, do well, stay
I want a
consistent,
good score.
and focus when I'm teaching.
Magnesium sulfate heptahydrate? No, but I know
We talked
chloroform.
Hydrates, and you brought up a very good term. What did
Remember
you
the
talk about
basics?
in the second
You don't
one?
have to wish. You can learn them right now, bro.
Hemiacetals and acetals.
Hemiacetals.
So it's basically the same thing. And the like the al ending, right? Al means we're working with aldehydes mainly. This mostly happens with aldehydes. So hemiacetal.
How much chloroform do I need to knock out a
/acetal.
child in
Hemiacetal,
Minecraft?
acetal, right? So this is when we, instead of water, we use alcohol.
Oh. Alcohol. R is just any functional group,
So
by the way,
we
guys.
get protonation.
Not to be confusing. R is not a chemical. R is just a functional group. This is how we abbreviate stuff in OChem because chemists are lazy. Scientists are lazy people. I think. Mostly.
Protonation of the carbonyl oxygen by
Real.
the protonated solvent, correct? We had a reversible process which creates this.
It's breeding. It's breeding with the alcohol.
We will get ROH,
In the
now
water.
a good nucleophile because this is primed for attack, to attack there. And we get ORH and OH. And deprotonation of this by the solvent
Ooh.
yields HOR, OH. OR and OH on the same carbon means what? Means acetal. Sorry, hemiacetal. It's half. Hemiacetal. Half an acetal. Hemiacetal. Half. Half of what? Well, the OR is what makes it an acetal. So it's half of that. If both of them were OR, it'd be an acetal. One of them's an OR, it's a hemiacetal. So how do we make a full-blown acetal? We take that and we keep reacting it.
For this one, okay. You need your aldehyde to pluck off something from a water molecule bonded to a functional group that gives it a positive charge to prep it. Oh, okay. Did the same thing with the other one then. I feel like it kinda is. Cause you somehow get an H on it, yeah. Yeah.
When you have this, they're leaving. Where the electrons here kind of give this guy the boot. Hey, fuck off. Get out of here.
Wait. I want to see that again.
R and OH on the same carbon means what? Means acetal. Sorry, hemiacetal. It's half. Hemiacetal. Half an acetal. Hemiacetal. Half. Half of what? Well, the OR is what makes it an acetal. So it's half of that. If both of them were OR, it'd be an acetal. One of them's an OR, it's a hemiacetal. So how do we make a full-blown acetal? We take that and we keep reacting it.
You gotta kick it off and tell it to go fuck off.
Lost. Because it doesn't look like that's going to keep reacting, but it will. Because you have this OR, OH, and instead of protonating the OR and going backwards, why don't we protonate the OH and see what happens?
Bath salt? I never used bath salt before. I wouldn't know.
So, ROH2 plus
7 hydrates so that I can react in water and make bubbles.
and make another molecule of ROH on the side along with OR and OH2. And now that that's a good leaving group, instead of making the carbocation, let's do a very famous biochem move, very famous upper level orgo biochem move called assisted leaving. Not assisted living. Assisted leaving. Where the electrons
Assisted
here
living.
kind of give this guy the boot. Hey, fuck off. Get out of here. You're already a good leaving group. Get out of here, right? So that guy gives that guy the boot, right? And we get
Bop.
wow. That's impressive. Why is that impressive? Because now look back to the first reaction.
Yeah.
We basically have the beginning step of the last reaction, but with an R instead of an H. That's incredible. That's really cool. That the solvent completely changed the way this is. Because normally, you can't get an R to attach to a carbon-no-carbon like that. You can't. It's just not going to happen.
Yeah.
Right? Unless the R was positive.
The plot
and somehow it got
thickens for
attacked or
real.
something like that. Like, and plus, that's not, like, when you have this. Sorry, I forgot my H. When you have this, and if you had this,
There's no way.
that's not even like negative enough to attack there. So it's so hard to do that, but now we just did. Right? We just did.
Wow.
And now you might be thinking, well, we kicked off this water. Wouldn't the water just attack back right here? Isn't that what we've been seeing all this time? But you have to think. You have to think. When we do a reaction like this, the water came from where? It came from the beginning when we were working with this guy.
Yeah.
The water is that. It's this oxygen that got protonated twice by the alcohol, right? So both those this is where your knowledge of atom tracking needs to come in. That oxygen is one of these original oxygens that got kicked off, and both those hydrogens came from the solvent. Right? You need to be cerebral enough to see that. And if you're not, it'll come with practice, I promise. Right? So why wouldn't the water just come back here? Well, we know that this water, that oxygen, came from the solvent. It came from the reactant. What do we have more of, solvent or reactant? The solvent is always in like 10,000, 100,000, 1 million time excess, right? So if we have one of these, we have a million of these. So which one's more likely to attack?
OH.
The ROH. Fine. Tayyib. Done. Right? H, O, R from there, and O, R, H from the solvent.
And then it gets deprotonated.
And now ROH
Wow.
solvent will deprotonate. Why does solvent deprotonate? Because there's so much more of it than everything else. And
That's a good way to think about it. Because I was also going to say with the H2, it'll just come back and hit it.
Is a full-blown acetal.
Whoa.
Everyone clap for the acetal. Yeah, you made it. He's so cute.
He is cute.
I love
So
him.
cutiful.
When it's with aldehydes, it's called acetal. When it's with ketones, it's called a ketal. Hemiketals and ketals. I'm not going to draw out the whole thing again. Replace the H with a CH3. Happens a lot more with aldehydes, though. They're more electrophilic than ketones are. Why? To further solidify our conversation, right? It has nothing to do with the sp2 character of whatever's going on, right? We know that these are both withdrawing groups, slightly negative and slightly positive, right? Slightly negative, slightly positive, right? Why is this more electrophilic than that? It has to do with the CH3 group on it, right? The H versus the CH3. Remember what I told you about R groups? R groups are donating. They donate some electron density onto there, so it decreases the electrophilicity of that carbon. Does that make sense?
Oh. What does it donate?
They donate some
R group.
electron density onto there, so it decreases the
Okay.
electrophilicity of that carbon.
Okay.
Does that make sense?
Got it.
Good.
So it's more likely to happen
You
with
can
the
explain everything. You
aldehyde
can
just
explain
because
all
it
of
doesn't
it.
have the
I
R group
promise you can explain all the
donating
very, very basic
like
chemistry.
electron
Do
density.
you remember a
Yeah.
couple basic rules?
Ah. なるほど.
I don't really like this one that much, but we should talk about it because it'll come up every now and again just in nomenclature.
Yes, electron really means they want more electron.
Don't put your pencils down. I do not want you to copy this. Just look at it once. It's going to come up in your Anki, and it might come up on a couple practice exams, and you just got to memorize it. But you don't need to know the mechanism or anything. If you have ketone, right?
Yeah.
And you have NH3.
Yeah.
I hate this mechanism so much. Because it's like, it's not even primed, and I refuse to believe that this happens like this because the end's just not strong enough to get the oxygen to do that. I feel like you should have NH3, NH4+. And then get like the protonation there. Like that's what I think. But in the book, it's just written as NH3, so that's what I'm going to show you. Right?
Oh, is this to make an amide? I don't like that either. Ugh.
Proton transfer. How many steps? 2 steps. Why isn't it 1 step? Because 1, 2, 3, 4, you don't make 4-membered rings. All right, 2 steps, proton transfer. OH, NH2. Right? I also don't think that will happen, right?
That guy with 3 legs? Yeah. Like a human. Like a girl with a skirt.
And then blah, blah, blah. And then obviously the OH picks that up. And you get this guy, which is known as what? This is an imine. This is an imine. Very funny name. That's an imine.
Amine. Ah.
And I think that's an enamine. Imine, enamine. Let me make sure. Yeah, nitrogen on top of a double bond. Imine, enamine. And you can tautomerize between imines and enamines. You can get a tautomerization, just like you can get keto-enol tautomerizations, right? How do I think this reaction is going to happen in reality? Once again, don't copy this down. This is just for the sake of learning how organic reactions work. I think you put a little bit of H plus in here.
Right.
Catalytic. And the H plus takes this and does that, and then that primes this to go like this. And then
Organization.
once you get this, you get that. And the solvent takes that away. And you get this. And then you get that. And then the H2O or the NH3 in order to remake the catalytic solvent gets you there. Quick orgo. Orgo on the fly. Okay. That's how you make an imine. And then that can tautomerize into an enamine. What is a tautomerization, my orgo people?
He accidentally draw 3
imine?
legs.
Quick orgo.
Oh no, that was a bond. That's the
orgo on the
NH bond. Got it.
Yeah, it's basically is when you have this and you can either put it in. Yeah, it's basically like resonance within a molecule when you put it inside of a base, right? So basically a keto-enol tautomerism is when you have this and you can either have acid or base. Base is easier, obviously, right? Because you have this hanging H. And what's going to happen is that your base what's that? What is that the first step of? What reaction?
What's
This
it
is
at
the
that?
first step of a very, very famous reaction, especially if I go like this. The aldol reaction. This is
Aldol.
the first step of the aldol reaction.
Aldol.
From the base. Enol. Ketone. Keto-enol tautomerism. In the same sense, in the exact same sense, imine, enamine. Except you need a stronger base. You'd probably need sodium amide. Enamine tautomerism. What's more stable, enols or ketones? Ketones.
Ketones.
Very good. Why?
The resonance?
Why? Huh? Well, let's look. I love this chapter. This chapter like has like layers. You're just like peeling back layers of information. And it's only 8:36. Ketone. Enol. What's the difference? Huh? Whenever I ask you about the stability of something with a double bond, it probably has to do with the p orbitals.
Oh, p orbitals, not
the p
resonance.
orbitals here are here and here, and p orbitals here are here and here. P orbitals are electronegative. And if you take something that's electronegative and get it to fight with something that's electronegative, they're not going to be happy. Because the p orbital pulls, and then the oxygen pulls, and the p orbital pulls, and the oxygen pulls, and the p orbital pulls, and the oxygen pulls. Carbon just gives in. And it's like, hey, I got a p orbital, and I'm electronegative. That's sick. That's awesome. It's quite unstable. Not, kind of. Which is why, oh my God, I love this part. How do I do this again?
He's so happy, man. He's so happy teaching this that it's like it like radiates off, you know? I don't know if you ever had like shitty teachers or professors that seem like they hate their like what they're teaching. What sometimes it makes me think like, bro,
What is that again?
you should have just chosen something else to
That
teach
is-
if you hate this
it's
so much, you
oxidized.
know? Feels
It's
bad.
pyruvate.
Pyruvate.
What is this? Phosphoenol pyruvate. Phosphoenol pyruvate. Right? Because what is that? So let's get rid of the phospho, right? For one second. Everyone follow me on the board. Put your pencils down. Everyone, down. That's pyruvate. What would enol pyruvate be? That ketone would turn into an enol. You can't turn into an enol this way because there's a carboxylate right there, right? It has to go to the right. If that turns into an enol, it's going to look like this. This is enol pyruvate. If we have phosphoenol pyruvate, that is phosphoenol pyruvate, or PEP, P-E-P, the last step in glycolysis before making pyruvate. So watch this. The formation of pyruvate from phosphoenol pyruvate makes what? Makes ATP. And we said when you make ATP, in order to synthesize that anhydride bond, you need a equal transfer of energy, right? And this is pyruvate kinase, right? Now, it makes sense, it kind of makes sense, right? That clipping this phosphate bond will give you energy, right? Because you're getting charge separation and you clip a bond and it creates energy, right? But that phosphate bond, it's not like connected to anything else special. We have to make what? We have to make
Phosphate anhydride?
We have to make that. And that bond, this bond right here that we're making, is a lot higher energy than that bond, right? Because look, there's a withdrawing group over there, and there's no withdrawing group over there. This is donating there, so it's a little more stabilized, right? So where do we get the rest of the energy from? Well, this is how the reaction happens. Ready? So first, the phosphate gets clipped. Phosphate gets clipped off, right? Minus Pi. No Pi over there, sorry. So first the phosphate gets clipped. And now you have a free PI that's in the enzyme next to the ADP waiting to get attached. What is that? It's an enol, right? And what is that? It's a ketone. And if the enzyme helps the enol pyruvate turn into ketopyruvate, since that's favorable and less energy, it releases enough energy to attach that phosphate onto the ADP. That's a coupled reaction. Isn't that fucking wild? Isn't that... You would never think... Like, no one would ever think. But you know who did? Professor Malitsky. Professor Malitsky did. He thought. Everything. Everything I know. Every single fucking thing I know about chemistry, that man taught me. And now I'm teaching you. And you'll teach someone else. And they'll teach someone else, and they'll teach someone else. And this is why when I die, I won't truly die.
That's wild.
And neither will Professor Malitsky.
He's getting He's going all
He
philosophical.
taught like an off-campus course that you like paid for. Very worth it. It was like $750 a semester for like 40 of his lectures. It was fantastic. Florida. Yeah, he moved. Sorry, guys. You missed the boat. But yes, okay, so the addition, this phosphor anhydride bond is facilitated by A, the hydrolysis of a phosphate bond, and B, a favorable keto-enol tautomerism. That's a very common theme. Coupled reactions, right? We'll talk about them a lot. Let's see if there's anything else to cover in the chapter. We did imines and enamines, right? I talk a little bit about carbohydrins. That's just when you have a cyanide that attacks and then like connects, and it's basically just a hydrate or like a hemiacetal with cyanide, right? Oxidation of aldehydes forms carboxylic acids. Very good. And reduction of ketones.
But
is
you know what,
normally
Usa?
done
That
with
goes for you too,
lithium
streaming and
glucarate.
learning with him.
Or right, depending on how aggressive you want the reaction. One last
How
thing.
did you know I was gonna
and we'll
nuke
go.
Lavon?
If
You
I-
read me to shame, bro. What the heck? What the heck?
We stated
You know, just because you said that, I won't nuke
that
it. I won't.
aldehydes.
What is reverse psychology?
The green.
So
You guys see the green properly?
no,
Better than the red or worse?
worse.
Okay. We stated.
What the?
I
Please,
don't like green anyways.
yay! Wait,
We
wow,
stated
he
that
loves us.
aldehydes
Ow.
can react. What'd you say? Fuck off. It's like, okay, I
You
have
nuked
this
the Modern
conversation all the
Channel.
time
Do you like
because,
them?
I studied philosophy, and it's a conversation I had with my philosophy professors, and it's just like, how do you know, bro? How do you know? Are you asking me how I know? How do you know? How do you know you're not wrong? Huh?
Clocked
Prove
it.
Prove that's red. Prove it. What color is it? If I ask all of you what color this is, right? It's red, right? Even I would say it's red.
It's
But
black.
here's a philosophical
No, I'm just
problem.
kidding. I'm not colorblind.
So two dudes are having a little chit chat, right? And they're looking at a tree. Like, oh, look, great tree. And the other dude's like, oh yeah, awesome tree, dude. Great leaves, great bark. Look at that squirrel, fantastic. Another dude comes around, he's like, oh, that's a fucked up looking dog, right? And the dude walks away. And the two dudes are like, fuck is that guy on about, right? Can you prove him wrong? Can you prove him wrong? No, because what I want you to think about when you go home tonight is that our preconceived notion of perceptual reality is rooted not in fact, but in linguistics. There are no facts in the world around you. It is purely rooted in a collective unconscious that buys into the principle that this is called red. There's no factual information about this being called red. So it doesn't matter what I call it, I see it how I see it, and you see it how you see it, and neither of us can prove each other correct. And we never will be able to. And that's why I'm not wrong. Right? So go think about that when you're home tonight. That there exists no factual information in the world around you. None. Everything's made up.
No, because he freaking mansplained essentially why he was right, or why he wasn't wrong though, which is essentially like him being right.
Acetal
Is that not
and
crazy?
hemiacetals, right?
I'm sorry. Was that not? Are you making fun of me? No. I'm thought that was so fucking big brain of him, bro. That was so fucking smooth. He fucking schooled his goddamn students. I was not paying attention to OTR. That was so good, bruh. That was so fucking good. That was aura. That was aura. You know what? Fuck all these chemicals. Fuck all these reactions. I care about the aura farming, man. Take something away from life. You can know a bunch of fucking random facts and shit and whatever random knowledge, but if you can't freaking apply it, which in this case, he took all the fucking philosophical shit he took to like school this kid. Like, that's so cool. I should just apply linguistics and say you got a 528 on the FCAT. You wouldn't be able to prove it though. I couldn't prove that I got a 528 on the MCAT either. Whatever number I see on my screen could totally be made up, you know? Just kidding. I'll get back to that. I'm sorry. Someone get my sorry counter on there. I think I'm at like
Is the aldehyde.
50 right now.
What if, right? What if we had a little guy, a little silly little guy, right, who looked like this? 1, 2, 3, 4, 5, 6. Aldehyde and ROH.
Aldehyde? That's not aldehyde, is it?
Interesting, right? So what if we had... Oh, sorry.
Oh! Clocked it!
Aldehyde and ROH.
Yeah.
And we take this funny little guy and we put him in a solution of acid. So what happens is...
Oi?
Pens down. No writing this. None. Because we're going to write it so many times in the future. And you'll see why. So that guy, 1, 2, 3, 4, 5, 6-membered ring.
Arigato.
This guy's going to fucking jump off a cliff. All right. 6-membered ring.
What?
Here. 1, 2, 3, 4, 5, 6. All right. So 1, 2,
Ring?
3, 4, 5, 6. Right? On carbon 2, this is number 1. On carbon 2, we have a methyl group. Carbon 3, 4, 5, 6. 6, we have this OH and a hydrogen. The hydrogen can go bye-bye. And this has a hydrogen on it. And that will get deprotonated, and you will make...
What?
So what's the hemiacetal?
Did he forget to charge
It's
on it though?
This carbon has an OH and an OR. It's just in the same molecule.
Hemiacetal.
You guys ready for me to blow your fucking mind again? Does anyone know where this...
Pause. You just made a hemiacetal acetal? Hemiacetal from a ring? That's why Usa Sensei is a little bit fucking confused too. I might have gone back to being the gakusei. Okay. 1, 2, 3, 4, 5. 6. 6 carbons, right? This electron... Oh no, you protonate this first because you dump this shit into an acid. Then you take this and then it goes to 6. Carbon 6. Shoot, goes up, boop. And then you have OH. Okay. Got it. Oh, I thought he forgot his charge. And then since you have this, all he did was he rotated it. Well, actually... No, because then wouldn't there be a charge there still? There'd still be a charge there. Where did his H go here? Does that make sense? Because if you deprotonated that H, then this would have like a minus charge in it, would it not? Am I tweaking out? Am I tweaking out?
This is going? You know where it's going.
I don't know where this is going, bro.
Yep.
Yes, acetal.
Glucose, in its straight chain form, is able to get protonated and attacked and form a hemiacetal. Where
What?
the closed chain form of glucose, the ring form of glucose,
Hemiacetal.
which looks like this, we'll draw beta D glucose. And there you go. OROH. That is a hemiacetal. That is a hemiacetal. And sometimes, when other sugars come along and attach there, you can get full-blown acetals. So glucose is a hemiacetal. And specifically, it's this OH right here. 1, 2, 3, 4, oh, sorry, not that OH.
You know what?
This OH.
If your brain is fried, I think mine's is too. I think we should watch that again. I think we should watch that part again. That's my number one
right.
forte.
It's
If
right,
you don't
right.
understand
I would say
something,
it's right.
just go back
But
until you
here's a
do.
philosophical problem. So you're home tonight. That they're
Okay.
Pens down. No writing this. None. Because we're gonna write
None.
it so many times in the future. And you'll see why. So that guy, 1, 2, 3, 4, 5, 6-membered ring. This guy's gonna fucking jump off a cliff. All right, 6-membered ring.
Okay.
All right, follow me here. 1, 2, 3, 4, 5, 6. All right, so 1, 2, 3, 4, 5, 6. Right?
1, 2, 3.
On carbon
5.
2, this is number 1. On carbon 2, we have a methyl group. Carbon 3, 4, 5, 6. 6, we have this OH and a hydrogen. The hydrogen can go bye-bye. And
Okay.
this has a hydrogen on it. And that will get deprotonated, and you will make
You forgot.
So what's the hemiacetal here?
Carbon.
It's this. This carbon has an OH and an OR. It's just in the same molecule. You guys ready for me to blow your fucking mind again? Does anyone know where this is going? You know where it's going. Yep. Glucose, in its straight chain form, is able to get protonated and attacked and form a hemiacetal.
This gonna pluck off an H. And that's gonna be plus. And it's gonna do essentially what this does.
Where the closed chain form of glucose, the ring form of glucose,
Yeah.
which looks like this, we'll draw beta D glucose. And there you go. OROH.
ROH.
That is a
Hemiacetal. Does that make sense? Does that make sense? It's okay if it didn't. Let's take a look at this. Shall we? Shall we, gang? Okay. I want to draw this out. Because I think that's my favorite part of OChem. I love drawing. Wow, that's not a given. That's so ironic. Because I never draw now. But, okay. それでは H O that carbonyl, that aldehyde. Okay. Have OH. How many lines did he draw? He drew 1, 2, 3, 4. 1, 2, 3, 4. Sorry for the uneven spacing. For everyone with OCD, I apologize profusely, but I'm not sorry enough. I'm doing this with my hands. And I have very shaky hands. Oh god. H, H. K. H. O, H. O, H. H. What happens is there's 2 electrons here. There's always 2 electrons here. Let's say you have some strong acid like H. Not strong acid, but decent enough. That's willing to give away its electron. Right? This is gonna take it from this. Sorry, never do this. Never do this. Never. I should technically be drawing the bonds out, but like, I'm not that picky about it. Okay, once it does that, then this is going to become. Me. Okay. Once it does that, this is gonna essentially become OH. Bonded to OH, right? And then there's gonna be a plus charge. And what's essentially gonna happen to that, I believe, is that it's gonna go through that same reaction again, where this electron pair, I think, right? Here. Sorry. Go here like this. Up like this. Then I'm gonna have OH plus. Then you're gonna have this by OH. This OH. This gonna go this. Right? Right. This go like this. This go and this and this OH like this. Oh, it's the 5th one? 1, 2, 3, 4, 5. Ah, because it's D, right? Ah, okay. Ignore me then. Probably this one. Because this one is the specific example for D-glucose. Okay, which makes sense. So this is gonna go here instead. Got it. Okay. So got cut. Got it. And that's that. That's how you make D-glucose then. Wow. Amazing. And you just have to deprotonize this. Why is the 5th in this? Why not the 6th? Well, in this case, it's because you want D-glucose, right? In a hypothetical scenario, I think there could be, like, what is it? The 6-glucose attacking, but that would make a completely different structure, you know? So, I think that's why. I also think maybe it has to do, glucose is also the 5th. Does it have to do something with stability, then? Possibly stability? Because a 6-member ring would be less sterically hindered than a 5-member ring. Is that why? I just assumed that would be my explanation. Maybe someone actually asked him that though. Let's find out.
That is a hemiacetal. And sometimes, when other sugars come along and attach there, you can get full-blown acetals. So So glucose is a hemiacetal. And specifically, it's this OH right here. 1, 2, 3, 4, oh, sorry, not that OH. This OH, the penultimate OH, as Professor Malitsky would say. Penultimate meaning one before the last. 1, 2, 3, 4, 5, 6-membered ring. Yeah. Glucose is your middle finger. So the thumb is the aldehyde, right? And you put the middle finger up and you put it against the board. Your fingertips are the OHs. And your wrist is the last OH right there. Like that. Right? So if you ever want to draw glucose, flip off the page, draw in your OHs. With your right hand. So glucose is a hemiacetal, right? Flip off the page, like that. Right? So if you ever want to draw glucose, flip off the page, draw in your OHs. With your right hand. So glucose is a hemiacetal, right? Which means that it can go forward and go back and go forward and go back. And it does that about 1 million times a second. I'm serious. That's what Professor Malitsky told me, that happens 1 million times a second. And I believe him. He could tell me 2 + 2 is 5, and I believe him. It doesn't matter if 2 + 2 is 5, because nothing's real anyways. I took a metaphysics course in my senior year for my philosophy major. And if you guys have an extra course lying around when you're seniors, it is quite difficult. Like, it's hard to get an A in, so like I wouldn't recommend taking it if you care about your grade. But like, if you ever get interested in philosophy and just want to talk to some philosophy professor, talk to Professor Sam Trivedi. He's fantastic. He teaches the metaphysics course here, and it's super complicated. We like had so many discussions about like what's zero, what are abstract concepts, what are colors, what is emptiness, what is nothing if there's still air in there, what is a hole? Is a hole the opening of the hole, or is it the thing within the hole, or is the air in the hole? Like, it's crazy. It's like the study of ontology, which is the nature of reality. It's beautiful, beautiful course. Anyways,
Thanks, goat. Sorry to cut you off, my goat. But, okay, OTR. I was right. Or, I was not wrong. I feel like that's better to say. I was not wrong. According to ResearchGate. Okay. The 5th OH group on the glucose attacks the aldehyde because this interaction forms a stable 6-membered pyranose ring. Sounds like what I didn't pay. Yep. Yeah. 5 and 6-membered rings, it would be more likely that the OH either before that 5th one or that 5th one, or 1, 2, 3, 4, sorry. That 4th one is, what is it? Is it right? 1, 2, 3, 1, 2, 3, 4. Yeah. So essentially, this one, maybe I should refer to it by carbon. Would it be easier by carbon? 1, 2, 3, 4, 5. Okay, OH on carbon 5 or on carbon 4 would be better than this one, because essentially 5 and 6-member rings have minimal ring strain compared to 7. If you had a 7-member ring, that would cause a lot of steric, or that would be very energetically unfavorable, and it's unlikely to happen because of that. And like, actually trying to say like whether or not what is it, one happens over the other more often between the 4th carbon and the 5th carbon is a little bit more, I think, would I say arbitrary? Or I can't really say exactly, because the thing is, the molecules are just going to crash against each other and do whatever reactions, right? Until they get to whatever desired product there is. I don't think there's anything that really like signals like, hey, OH on carbon number 5, make make D-glucose. I don't think that's a thing. Also, hi Rave. Hello. Do you want to learn OChem with us?
That being said, now that I've literally given you a biochem lecture
Hexagons or
instead of OChem,
vesticons? Mm-hmm. When in
thank you
doubt,
guys so much
6.
for listening.
6. 6, 6, 6.
8:51. Had a great time. I'm really happy I got to
Yay.
do this lecture. And next time we will talk about enolates and anions, which is very, very important because we get to talk about the aldol reaction, the Claisen reaction, and all that stuff. Then we'll talk about carboxylic acids. That goes super quick. Carboxylic acid derivatives we pretty much did, but we'll glaze over them once again. And then after that, it's all stuff that I don't teach you. So it's nitrogen-containing compounds, which is literally just like 15 minutes of a lecture. And then it's spectroscopy, which I'll send you videos for. And then we will save lab techniques. There's a chapter on lab techniques. We will save it for when we're in the practice phase, because you're gonna fucking forget. You're going to forget. And lab techniques deserve their own like dedicated time. Like, let's do questions. Let's talk about the lab techniques. Let's talk about how they work. Blah 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 blah. Thank you guys so much for listening. Thank you for watching back home. Thank you for keeping up. And I'm very happy to be back. I'll see you guys next time.
Yay. Guys.
We are live.
Holy.
Welcome back.
Oh, okay. This is resonance. This is like... Thanks for the class? No! Class is not dismissed! Class is not dismissed! But... That's you growing your attention span, man. Wow. See, you guys sat through that. We sat through that. We fucking sat through that. Awesome. Okay, this is the bread and butter, I feel like, of OChem. And a lot of kids, I'm doing some ADHD, I can't talk. ADHD thing. This is ADHD training. This is essentially what Adderall is. Oh, just kidding. With your stream on the right side and physics on the left side? Bro, you're like those kids on fucking TikTok that has like the Subway Surfer open and then like Twitter on the side and then like YouTube, then some other streaming service on the side. Which, by the way, guys, if you have Crunchyroll, I heard they got hacked. So you should do something else. On the Subway Surfer, am I like the narrator that reads the AITA while playing Subway Surfer? That's awesome. Thank you. But you see him giving me the side eye. Yeah, what did I say? Resonance is the bread and butter of OChem, and a lot of the reasons why I feel like kids failed or they had a hard time with OChem 1 is because they didn't understand resonance. I've never used Crunchyroll. I hated the ads too much to sit through it. Yeah, but maybe for this guy, I've been sitting through his ads. I hope he's getting paid well. I hope you're good, buddy. I would give you ad revenue money. Yeah.
Today, we're going to go a little off the cuff. We're not going to talk about anything.
This is fucking awesome.
Last time, we talked a lot about leaving groups, conjugate bases.
Richard
acid-base
Freeman, I'm
reactions,
poor.
blah, blah, blah.
I also will not
feel
give
like
in to
it was
capitalism.
appropriate to have a short discussion about resonance and factors that contribute to conjugate-based stability because it is such a big thing in the field of organic chemistry. So to begin, let's have a discussion about resonance.
Can you guys hear this? I feel like this is important. If there's anything you take away from OChem, it's resonance.
So resonance is basically defined as the delocalization of electrons through a p orbital system. And specifically, this is a conjugated p orbital system, right? And what does it mean for a p orbital system to be conjugated? This is one of those terms that's better in a diagram as a definition than it is in words. This is not a conjugated system. This is called a cumulated system. A cumulated system, where you have a p orbital like this that binds to a p orbital like this, And then you have one here that goes like this and bonds to one like this.
Oh.
And you have another one here that goes like this and bonds to one like this. Right? That is called a cumulated system, right? And ironically enough, resonance can't really occur through cumulated systems, right? But they can occur through conjugated systems. So what would a conjugated system look like? It would look something like this. Where those p orbitals only attach to one that's directly next to it. And your sp2 carbons are kind of staggered. Because you realize in the cumulated system I just showed you, in this example, yeah, those end carbons are sp2, but what about those carbons in the middle? Are those sp2? No, they're not, right? Because they have how many electron domains? 1, 2. And remember, do my trick. You throw down 4 letters. You're using 1, 2. That means the hybridization there is sp. And you have 2 free p orbitals. What are those p orbitals doing? Well, one of them is attaching to this carbon to the left, and the other one is attaching to the carbon to the right. Correct? Whereas if you look at the conjugated system, right, I drew out the p orbital map just so you can visualize it. But if you look at the conjugated system,
Conjugation has always been kind of confusing to me.
you've got sp2 and sp2 and sp2 and sp2 and sp2 all the way through. So now that you are good at identifying sp2 carbons, sp2 hybridized carbons, and understand, remember, we have what? sp-p-p. So all those have that lone p orbital, which we display in the p orbital map, right? You should be able to almost see this p orbital map in your head. You should almost be able to visualize it when you look at
Do
a
you guys
diagram,
get why it's
right?
sp2 though? Because the thing is, if you draw this out, right? I think what he was trying to get at was, you see how he drew out the sp-p-p? But then you only see 2 bonds, and then, or 1, 2. Then you're like, wouldn't that just be sp? But then, what is it? You also have a bond to hydrogen, I believe. That's not drawn. That would count. So it would be 1, 2, 3. So sp2. sp2. Got to say that.
Okay. So, that being said, if you can see this and you can see that, you can merge the pictures and understand that conjugated systems are basically just lines of sp2 carbons or sp2 atoms in general, right? And in real life, what do electrons do? Electrons move through what? Electrons move through wires, right? And I want you to think of conjugated systems like wires, like little wires that connect parts of the molecule together, that electrons are capable of moving through. Is that jacket from Uniqlo? I love Uniqlo.
You're getting sidetracked, bro.
And so's the shirt. The whole outfit's from Uniqlo. And my hat. So, you see this, and now we're going to build on that understanding. So we know that electrons can move through conjugated systems of p orbitals, lines of sp2 atoms, correct? But the electrons don't really want to move here. There's no reason for them to do so, so they don't really do it. When would they do it? It's when there's a disturbance inside of the molecule, when there's a problem, right? And resonance is really sweet, because it's the molecule basically giving up a part of its stability somewhere else for the sake of the whole molecule. It's a part of the molecule giving itself up for the rest, right? It's like one big family, right? So let's take a look at a conjugated system that looks like this. we have an electron deficient region in this molecule, right? And I want you to ask yourself, in your head, can you make a p orbital map of this molecule? Can you look at it and think, where are my p orbitals? Right? So so first we have to figure out what's our hybridization everywhere. And if you're not at the level to figure out hybridization by looking at that yet, let's dumb it down even further. This is inherently what we're looking at, correct? That's what we're looking at. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Positive charge on 5. Double bonds between 1, 2, and 3, 4. Right? This is what we're looking at. So now you'll be able to tell me, oops, hold on, 1, 2, 3, 4, 4, 4. There we go. It's been a minute since I did that. I usually just draw them out like this. So now you'll be able to tell me exactly what is the hybridization of all these carbons. Let's do this one. We got 1, 2, 3, it's sp2. Over here you got 1, 2, 3, that's sp2. And over here it's sp2. And over here it's sp2. And the carbocation. The carbocation. What are all carbocations? All carbocations are sp2. And if it is sp2, that means the carbocation has what? It has a free p orbital. Has a free p orbital. So this has a p orbital, and that has a p orbital, so does that, and so does that, and so does that. And 1 for each of them. And that makes this system of p orbitals what? Conjugated or accumulated?
Conjugated.
Conjugated. Very good. It's conjugated. Right? So that's number 1. Electrons move through wires, or p orbital systems. Specifically conjugated p orbital systems. Number 2, p orbitals are what? P orbitals are, I said it last week, p orbitals are electronegative. P orbitals are electronegative. Right? One more thing. In this molecule right here that I drew over, right? Can you guys tell me the geometry at each position of those carbons? What's the molecular geometry there? If it's sp2, it's trigonal planar, right? We're going to come back to that later, that trigonal planarity of an sp2 atom, because it's very important in biochemistry. Well, it's important everywhere, but it's particularly important to us in biochemistry. Right? P orbitals are electronegative. So if you can imagine, these p orbitals over here and this p orbital over here, they're fighting for the electrons, right? And this one, since this p orbital is pulling on the electrons and it has a positive charge, you want to donate to that positive charge, don't you? You want to donate some electron density to the positive charge. And the fantastic thing about conjugated systems is that they don't just donate. They don't just let someone borrow, they give. They completely donate. So what happens is that these electrons move through the wire. They go right here, look, electrons right here. The wire connects these portions, the electrons move through the wire. It's like this, and it folds over that way, right? So if we draw our resonance brackets, I'm going to do it properly. I'm going to show you guys how to do this properly, because I always want you to use a proper notation. You drop a bracket.
Bracket.
Whenever you're doing resonance, it happens inside of brackets. You use a double-headed arrow to move 2 electrons. You give resonance arrows, and you show what changed and what didn't. So none of this changed, none of the backbone changed. We have a bond here now, and the positive charge moved over there. Good? Yes. And then what else can happen? Because remember that when you're inside the resonance brackets, everything's frozen. So now this can bend over that way, right? So we can get resonance that goes like this.
Boop, 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 boop.
And that's how you know I've been doing orgo for a long time, when my bonds overlap like that, because I'm just too lazy to draw them properly. Because a lot of people will say, hey, Yusuf, this and that are the same thing. But no, they're not, if you freeze the molecule in place. These brackets freeze the molecule in place. And what I'm saying to you by drawing this is that the positive charge is shared between positions 1, 3, and 5 on this molecule in free space. When it exists as a hybrid of all three of those structures. And the question we have to ask ourselves is, which of those three structures does it look the most like, and which of those three structures does it look the least like?
Oh, he's cracking a Celsius. Bro is
Those are
tired.
major and minor contributors. Who can
No.
tell me what the major contributor is here?
Poor bro.
This one? Why? How does it make it different than that one?
Actually, second one.
Why the second one?
Because it's in between two carbons.
So,
He needs a break
donate
for
to the
real.
poor,
Donate to the boy.
steal from the rich. Robin Hood.
Robin Hood for real.
Organic chemistry is very Robin Hood. What do we mean by the poor or the rich?
Electrons.
The electron poor and the
Electron
rich.
rich.
Is a carbocation electron poor or electron rich?
Electron poor.
It is electron poor, right? Here's your next rule. R groups are donating groups.
R groups are donating. They're the thing that's giving stability, kind
R
of.
groups are
I
donating
remember,
groups.
because we talked about that last time. That's what made
What's the
ketones
opposite of a donating group?
less reactive.
A withdrawing group.
Thievers?
Donating groups and
Someone
withdrawing.
said thieves.
So R groups are donating groups. And if R groups are donating groups, let's take a look at what's donating here.
Yeah, that's
So
why
this is an R
ketones are
group,
less
right? This
reactive
whole
than
thing.
aldehydes.
So that is donating to there,
Yeah.
right? I'm going to draw it like this without the thing. So that's donating that way. Here, we have an R group to the left and an R group to the right. That means we're donating this way and this way. And here, we're donating this way, correct? So what's better? 2 people donating to the poor or 1 person donating to the poor?
2 people donated.
2 people. So this has the most stability, which means this is your major contributor.
Ah. なるほど.
Not 2 double bonds, but 2 R groups in general, right? In the same sense that this carbocation is better than this carbocation. Better. Because what's donating here? Donate, donate, donate. 3, 2. Which would be better than 1, right? Yeah, you had a question or what?
No, so whichever one has more to steal from is the most stable.
Exactly. So that's the major contributor, which would make these the minor contributors. Now, we have to differentiate. If one of them is minor and another one's worse than that, that last one becomes negligible.
Usagi, move your ears.
But
They're
these
blocking.
look the same. So they're equally
What do you want
minor.
me to do?
So this is
Do you want
minor.
me to cut off my ears? What if I just... ごめん. My head's too fat. My ears are too big.
And
I
this
need them
is
to be big
minor.
so I can hear you talking shit, man.
So this might be 70%
4
of the
ears is not
structure,
enough, you know?
and
I
this
have to
might
make
be
them
15,
large.
and this might be 15. So what does the true structure look like? It looks like a hybrid between
Wow, Grandma,
all
what
of
big
these, where
ears
the
you have.
majority of the positive
Wow, how
charge
hairy
is
you
held
are,
in the
Grandma.
center of the molecule. So, if this molecule were to undergo a
My
reaction,
dear son.
if
Son, daughter, my dear daughter.
this
I don't want to
molecule,
eat you,
which is
but
also
I
like,
will.
it's actually
Wow. Look at it.
it looks kind of like that, right?
Yeah.
Plus 0.7, plus 0.15, plus 0.15. If that were to undergo a reaction with a nucleophile, the nucleophile would preferentially attack carbon 3. Carbon 3. Because it has what? It has what we call the most carbocation quality. Carbocation quality. The carbocation quality of carbon 3 is the most, well, it has the most, yeah. So the carbocation quality is highest in carbon 3. Does that make sense? Very good. Okay. So let's do one that's a little more complicated than that.
I feel like I just missed that entire section.
And this, and this,
What if they're both
then
bad?
that last one becomes negligible, right? But these look the same.
Oh,
so they're
okay.
equally minor.
They're
so
equally
this
minor.
Is minor. So this might be 70% of the structure,
70%?
and this might be 50.
50,
So
50.
if this molecule were to undergo a reaction, if this molecule, which is also like, it's
Yeah.
actually, it looks kind of like that, right? Plus 0.7, plus 0.15, plus 0.15. If that were to undergo a reaction with a nucleophile, the nucleophile would preferentially attack carbon 3. Carbon 3. Because it has what? It has what we call the most carbocation quality. Carbocation quality. The carbocation quality of carbon 3 is the most, well, it has the most, yeah. So the carbocation quality is highest in carbon 3. Does that make sense? Very good. Okay. So let's do one that's a little more complicated than that.
Wow.
Okay?
Wow. Whoa, 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 whoa.
Can you draw a p orbital map? I'm sure you can.
Yeah.
sp2, sp2, sp2. We've got
One
3
here,
atoms which
one
can
here.
contribute to the resonance,
One.
right? We've got the wire moving. Where's our wire? We've got our wire moving like this, right? That's our wire, just those 3. So this right side of the molecule is completely isolated from the wire. So it's not going to communicate. It's not going to participate in the resonance.
Mm.
So resonance can go this way.
About. Ew.
And a lot of people don't realize it, but even though it doesn't happen that much, resonance can also go that way.
Whoa.
Yep. So now we're
Why?
getting into lone pair resonance.
Lone pair resonance. なるほど。
And it's always better to have something with an octet than something without an octet. So this is the major contributor. But what do minor contributors do? Minor contributors tell you the site of attack on a specific molecule. Will you be asked the difference between these two? Not really. Because it's like, if you're here, it can resonate, but it doesn't donate as much because this is withdrawing. The BR is withdrawing. That's another thing. Halides / electronegative atoms are withdrawing. That's another thing. But then if you're here, it's like you get the secondary and you're next to 2 positions and it donates. So that's going to be quite difficult. You're not going to get a question like that. But I just wanted to show you that lone pairs off of other atoms can donate as well.
Write that down. Write that down.
What does this mean for reactions? So we're just doing carbocations because carbocations are the easier ones to understand. And then we're going to do carbanions because carbanions are going to land us into a discussion about conjugate bases and base stability. Because what are negative things? Negative things are nucleophiles or bases, right? So let's get through this first and then we'll move on. So what does that look like inside of, like a reaction? Well, we see it all the time. I want you to tell me what happens there. It's an SN1 reaction, right?
SN1.
It's an SN1 reaction. Why isn't it E1? Well, I didn't put a lot of heat in the flask. So at
Ah.
lower temperatures, SN1 predominates, and at higher temperatures, E1 predominates, right? So if we're going to get an SN1 reaction like that, let's take a look at what happens. Can I erase this? Cool. Am I writing big enough?
Yeah,
Can you guys read properly? Okay.
you're good. Oh.
Huh? You're used to it? Yeah, I know. I'm also used to writing small. All right, so let's take a look at what happens here. So we got a bromine, and we got that group right there. Right? Can anyone already tell where I'm going with this? If you can, you have really good foresight. Because I know where I'm going with this. Right? Let's put this in a solution of water, and let's let the reaction go. The first step of every SN1 reaction is the leaving group fucks off, right?
Yeah.
The leaving group leaves. And we get the slow step, which is the formation of the carbocation.
Cation.
Right? And organic chemistry students who learned SN1 will hop on this bandwagon and go, hey, I know what happens. Everyone put your pens down. Everyone, pens down. I know what happens. H2O comes here, and we get two products, one of which is the R enantiomer, and one of which is the
S.
S enantiomer. It's a mix, right? So then when we deprotonate both of these, we get that. And that looks like a perfectly good answer until your professor marks you wrong and tells you that this is a very, very, very minor product. Incredibly minor product.
Why?
But professor, I showed all my work. It's right there. The leaving group leaves and we get the carbocation and it attaches and we go. What's wrong here?
Is the water just
You guys
gonna...
remember, it's a very small fact about
Or-
organic chemistry that's easy to forget. Whenever you make a carbocation, the carbocation is greedy. It is greedy to be in a better position than it is now. And remember that the molecule will sacrifice itself to save the carbocation. If there is a hydrogen next to the carbocation on, good timing. If there is a hydrogen on the molecule adjacent to a carbocation, and that hydrogen is on a position that is either more substituted or more stable than the position that the carbocation is currently on, you will get what's called a hydride shift or a proton transfer. It is more commonly called a hydride shift. And this hydride shift is an intramolecular movement of this hydrogen to stabilize the carbocation in two ways. Number one, to get the positive charge off of the less stable position and move it onto the more stable position. So we get that.
That's crazy.
And that is why your organic chemistry professor marked you wrong when you put this as the answer. Because that doesn't happen. At least not the majority. Maybe 1, 2.
What the hell? What the hell?
90+% of the solution, the
Is
carbocation
H-shift?
turns directly into that. Why? Why? Because remember, we're in terms of delta H, in terms of energy, we're trying to go down, right? That first carbocation has an energy up here. The moment it sees that hydrogen, it can snap it and drop it down here. So if it goes down in energy and becomes more stable, that's better, and that will happen. And that contributes to what? So the negative delta H here also contributes more to a negative delta G. Anything to make the delta G more negative. Anything. Anything for the delta G. Thermodynamics. It's all thermodynamics and acid-base
Anything for the
reactions and
G.
thermodynamics. It's all you have to know.
Wow.
Right? So that hydride shift stabilizes the carbocation. How? By the ways that we spoke about before. Because here you have 1, 2 donors. Here you have 1, 2, 3 donors. It is also very good etiquette to show your hydrogen after it is shifted. It is very good etiquette, and your organic chemistry professor will love you for it. because you make it easy to show you know where things are going.
It's beta hydrogen, right?
Huh?
Or I'm wrong. Is it beta hydrogen, right? It's called beta hydrogen.
Yeah, so this would be an alpha hydrogen because that's the carbocation position. We'll talk about like alpha beta when we get to later in orgo. Because we're going to have to do like aldol reactions and Claisen reactions, et cetera, et cetera.
Just the point that says R groups are.
Donating groups. And halide/electronegative atoms are withdrawing. So that is a more stable carbocation. And if it's more stable, that's the one that's going to move forward. Do you guys mind if I make this concise and I just say minus H plus? Attaches, retract the H plus, right? Do I need to put plus minus there? Is that chiral?
No.
Where? It is not chiral because this has an ethyl group, an OH group, and 2 methyl groups.
Bingo!
Not
Bingo da zeh! Freaking do it.
Does that make sense? Carbocation rearrangements make sense? Yes? All right. Plus minus means it's a racemic mixture. You get the R enantiomer in the same amount as the S enantiomer. How do you make it not a racemic mixture? You have to use a chiral solvent, like BNAP. But that would not come up on
Lecture check. Are you guys awake? Are you 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 awake? Ah! Ah! Hi. Hey guys. Just make sure you didn't fall asleep during class. I'm not sleeping this time. よかった. 3 physics. 素晴らしい. No. I think everyone else fall asleep. Hey, gold star for you 3. You 3. Kimchi gudonkers and RTO. Can you change your name to PTO after we're done? We're getting physical. Galaxy friend. Is he helping you? Are you helping him, Rave?
All right, so we talked a little bit about SN1. I will now show you guys the reaction that allowed me to best understand all of these trends of organic
Very
chemistry.
cool.
All these trends of resonance. And if you take Orgo at Brooklyn, they emphasize it very heavily, but I don't know if you guys remember it. It's called the pinnacle rearrangement.
Pinnacle. You talked about this last lecture. Oh,
You guys
hell
did a
no.
lab, and the lab was called the pinnacle rearrangement. And the whole point of the lab was to teach you the rules of resonance with carbocations. This is the lab. You begin.
That was like a horse or like a dog. What the
with an
hell?
alcohol that looks like this.
Ugh.
And you place that alcohol in a solution of sulfuric acid.
So
Very
furious.
dilute. And I think a little bit of water as well.
Can I move this? Gomen. 止まって。待って待って。
Acid and water or water and acid? You guys got to review your lab techniques and safety. All right. So what's going to happen here? Well, the H2O gets protonated by the sulfuric acid, right? So let's say that we have some free hydronium being cool, floating around in this flask. These markers are really nice. I like the little, the pointed tip ones.
Give this guy some better markers, please.
Thank you. So, it's going to protonate either the solvent or, finally, the flask could grow a pair and make the reaction happen, right? And we get protonation of one of those OH sites.
Yar.
And we create a water adduct, which serves as a very good leaving group on that position. And this looks like it's setting up for another SN1 reaction, and you wouldn't be wrong. You absolutely would not be wrong. Because now you basically just have a good leaving group and a solvent, a polar protic solvent. Right? Did you do that thing I asked you guys to do last week or on Tuesday? We'll go over it later. Out of everyone, I expected you to do it.
The thing is, I'm only in Orgo 1, so
Ah.
I don't even know, like, just from synthesis.
Oh man, that's tough.
So I tried looking at it, I was like, there's no way.
That's tough.
So,
What's up, buddy?
without Google, it's not really.
No, that's definitely like an upper level Orgo 2 sort of thing. But we'll go over it later, and I think it'll make a lot of sense to you. Because if you understand the whole leaving group thing, then it's good. Okay. So now we have what's setting up for an SN1 reaction. So what happens in SN1 reaction? We get the formation of the carbocation.
Bye-bye.
I'm going to draw it this way so that I don't need to hunch my back and like bend over and everything, because this is important. This is the important part of the reaction.
Bend my back. Plus,
And that basically forms another water, right?
yeah.
So it just adds to the solvent.
Uh-huh.
Okay. Cool. Very good. And now everyone freaks out. What do we do now?
Proton shift?
We made the water so the water can go back. But if the water goes back, we go back. And then we come back. And we go back and we come back. And we go back and we come back. And no one knew what to do. So some people were like, wait, you have sulfuric acid in the flask, which is deprotonated. Why doesn't the sulfuric acid attach there?
That's
Sulfuric acid is a very strong acid, which means its conjugate base is very stable. It's not going to want to do that. It's really stable. And we'll get to why later. That's part of this lecture. So we can't attach the water, and we're not going to do an elimination because it's not warm enough, right? So what's going to happen? The oxygen's going to what? Because you can't resonate because you only have one p orbital here.
Oh, we can't H shift.
That's a good point. A lot of us thought that when we looked at this, but that would make a 1, 2, 3 carbon ring, and 3 carbon rings are really explosive.
I think it's methyl group.
Hold that thought. So this is cyclopropane, or sorry, this is cyclopropane, right? And this is propane. If you use this in your barbecues, right? You light a propane tank, and then you light a little fire, and then you cook food with it, right? Professor Malitsky gave us this example to explain what cyclos are. If you filled a tank with cyclopropane instead of propane, your entire backyard and your entire home would be rubble before you'd even get to light the spark inside of the gas tank. This has a ridiculous amount of intrinsic energy, so you wouldn't want to make a 3-membered ring. So,
Oh.
remember
Don't fill the tank with
that
triangles.
the molecule would do
No
anything
triangles.
for the carbocation. Well, that's what I thought too when I looked at this. But there's no hydrogens here.
Right. No
It's
H.
a methyl shift. So this whole CH3 group detaches and moves.
That's
That is
so
called
fucking.
A CH3 shift.
Are you fucking kidding me?
A methyl shift. And that methyl shift creates this molecule.
What the
Or this
hell?
intermediate.
There's just a.
And there's the methyl group that you moved. Right there in the middle. This guy. So we moved. And now alarm bells should be ringing in your head like fucking church. They should be going off like wild. Because, excuse me, what the fuck? We were so okay over here because we had 1, 2, 3 donors. And now we have 1, 2 donors, but we don't just have 2 donors, we have a withdrawing group. Aren't we stealing from the poor? Isn't that what we don't want to do? Isn't stealing from the poor exactly what we don't want to happen? So why is this better than this? Because then you realize that I've been leaving out a small piece of information. That in this whole scheme, they told us to figure out the mechanism, but they gave us the final product.
Is there a double bond? Oh, I knew there was gonna be a
That's the
double
final
bond.
product.
Oh,
So what you realize is that this
Gah,
carbocation
okay.
is actually more stable because of one very important overlooked detail.
the electron. The electron can come
Lone
down.
pair resonance.
My mind is blown. My mind is blown.
And if you're looking at this wondering, why would oxygen become positive instead of the carbon?
So you know that?
Oxygen has a
Yeah,
higher
'cause he talked about it
electronegativity.
earlier.
You must be forgetting that carbon, when it's positive, doesn't have an octet, but oxygen does. And that, in my way of saying, is oxygen fronting the discomfort for carbon stability. Oxygen is okay being uncomfortable so long as carbon is happy with a full octet. All of you guys get that? All of you guys understand what happened here? We methyl shifted and went to what looked like a less stable position in order to gain resonance. And when we gain the resonance, we create an intermediate which is far more stable than not having an octet, and that intermediate is longer lasting and moves forward in the reaction with a deprotonation and forms this ketone. And when
Wow.
that intermediate forms the ketone, we finish the reaction. That's it. This is called
The pinnacle.
the pinnacle rearrangement.
Pinnacle. The pinnacle. The pinnacle of resonance.
I never wrote out the word rearrangement. I would show an arrow looping on itself. So when I said carbocation rearrangement, I did this. The pinnacle rearrangement. And if you'd like to look it up, you can. And it teaches you everything you need to know about carbocation resonance in chemistry. That donating groups are good, resonance is better, and intermediates can be part of the final product. Intermediates can lead to the final product, right? Even resonance intermediates. And what this tells you, what this specifically tells you, is that even though this is a tertiary carbocation, a secondary carbocation with resonance is still better. And even further than that, everyone thinks a tertiary carbocation is so stable. Professor Militsky ventured to say, and he's looked at so many research papers about this just to make this claim, he ventured to say that even primary resonant carbocations are more stable than tertiary carbocations.
Crazy.
So he strongly believed, and I agree with him. I didn't look at the research, but I trust his word. He believed that this was more stable than this.
Whoa.
And I trust him. Because how much stability could you really be getting from a donating group, right? Because this is what, a +1 charge? Let's say that each of those donations subtracts 0.1. You're resolving to 0.7. Here it's 50-50, 0.5 across two domains of the molecule. The charge separation, the separation of charges across the entire molecule, that sort of average of the whole molecule, is far more stabilizing than having a localized charge. Remember what we said at the beginning? Resonance is nothing but delocalization of electrons. Delocalized charges are far more stable than localized charges. Why do you think lightning falls out of the fucking sky? Because it's delocalizing. It is spreading itself thin. It is dissipating into the place it wants to go. Hopefully it's not through you. What are those scars called when you get struck by lightning? It starts with an L. No, it starts with an L. There's a specific name for it. Oh man, I forget. But they look like leaves and they like radiate like that. Lancaster or I forget something. Someone look it up. It's gonna bother me. Just look up scar when hit by lightning or struck by lightning, and it'll come up. It should start with an L. I was gonna say Leidenfrost, but Leidenfrost is like this effect that happens when you boil water and it like causes things to float on top of it. You guys ever put a wet pot down on the stove and it kind of floats? Huh? Lichtenberg, yes. Lichtenberg lines or Lichtenberg scars. Have you guys ever put down a wet pot? Like you just washed a pot and you put it down on the stove to cook with, and then the pot kind of floats on the stove and moves around? You've done that before, right? So what's happening is that the pot with the water droplets, the heat is coming into contact with the water droplets, and they're creating gas, and that gas circles up underneath the pot and circles around like this because it gets pushed down by the surface of the pot and then pushed back up because it's a gas, and pushed down, pushed up, pushed down, pushed up, and it creates a layer of gas that the pot just kind of floats over as that water's evaporating. It's called the Leidenfrost effect. I have a lot of random facts inside this head of mine because I watch a lot of shitty YouTube at 2 in the morning. Okay.
He's brain rotted too.
Do you guys think we're good on carbocation resonance? Because that's pretty much as complicated as it could get on the MCAT, right? So now let's take these same rules, because nothing changed. Let's take those same rules and apply them to carbanions and negative charges. Because those are the
And the
rules
brightest minds
of
get corrupted.
resonance.
True.
And it's not like chemistry
No one's
is
safe.
breaking when you change from a carbanion to a carbocation or a carbocation to a carbanion. It's the same rules for different people. MMA fighters, 200-pound MMA fighters, and 95-pound MMA fighters. They fight with the same rules. They're just different structures, different human beings, right? They fight differently, but they play by the same rules. Right? Yeah? Okay. So I was going to do one last thing. Oh, before we do, actually, let's do it after. So we talked about carbocation rearrangements, which I told you guys last week to remind me of, but I remembered. One more thing, I'm going to make a note of it. At the end, all the way at the end, we're going to talk about radical resonance. And radical does not mean cool. It means the actual resonance of radicals. It is quite cool, but it also causes cancer. So let's look at this. It is notoriously difficult to create carbocations without using bases. And it's sad, carbanions without using bases. And it's sad because we have to talk about bases in our discussion about carbanions. So it's like, it's an infinite sort of loop of trying to define one thing after another. So we're just going to hop into it. So whereas a carbocation has a deficiency, let's look at this. It is notoriously difficult to create carbocations without using bases. And it's sad, carbanions without using bases. And it's sad because we have to talk about bases in our discussion about carbanions. So it's like, it's an infinite sort of loop of trying to define one thing after another. So we're just going to hop into it. So whereas a carbocation has a deficiency of electrons, a carbanion is electron rich. Electron rich. So this is a carbanion. That's a carbanion. And I told you that R groups are donating groups. R group, R group, R group. But what are we doing? Remember I said 2 more rules. Donate to the poor.
The poor.
And steal from the rich.
Steal from the rich.
Fuck you, Elon.
Real! Say it louder, King. Lavelle.
Right? What are we doing here? Are we donating to the poor or the rich? We're donating to the rich. That's a problem. So these R groups are actually destabilizing the carbanion. So this carbanion is less stable than this carbanion is less stable, is less stable than this carbanion is less stable than this carbanion. And that's the absolute opposite of what we see in carbocations. Why? They're playing by the same rules, but they're different characters. You don't want to donate negatives to a negative being. You don't want to take away negatives from a positive being. You want to donate negatives to a positive being and take away negatives from a negative being. And in the same sense, this is less stable than this. Why? Halides and electronegative atoms are withdrawing.
So it's pulling.
Withdraw, slight positive, withdraw. You're pulling back that electron density. You're helping it out. You're helping that guy out. Even better, directly, right? Even better. But that brings up a curious topic on the MCAT, which you probably won't see all too much, unless you're looking at like mechanisms and stuff like that, which come up quite rarely, where this actually might not be that bad. Because of what? Lone pair resonance. Because of the fact that that can be stabilized like this. And for my Orgo 2 people, that kind of looks like the reaction that happens when you do a hydrobromination. When you have, and initially you get something like this, right? And then you attack the more stable side, the one that is more unstable as a carbocation but would make the more stable product, which is always that one, right? And then if it's a Br, it attacks there, you get a dibromide, and if it's OH, you attack there, you get an alcohol, right? Orgo people, Orgo 2 people, what's the only thing that you can do with this if you're starting a synthesis? What's the only thing you can do? Brominate it. Bromination with light, and then what's that going to do? It's going to attach it to the less or more substituted place. More. How do you get it to go less?
Radical? Heat light?
Peroxides.
Fuck!
Roar.
Damn it. Peroxides. And
Those come up on the MCAT every now and again, where it's like, what would the first step be? Or how did we get here, right? Because from here, you can go anywhere. Yeah, my Orgo 2 people know you can go anywhere from there. Literally anywhere. You can go Grignard, you can go ketone, you can go alcohol, you can go carboxylic acid, you can go anything you want. Good? Okay. So let's look at the resonance of carbanions.
yeah.
It pretty much follows the same rule, where you sketch out this p orbital map, right?
The orbital map.
Also, Orgo 2 people, I know you would just do the double jump at first because you can see it, but some people can't. Yet, but they will. Because all the Orgo 2 people are like, why even go through the middle step? It doesn't matter. And then this is going to come up this way, and go there, and come here. Right? I'm going to dial back over here. And we're going to compare. Same thing, different players. And we said before that this was the major contributor, and those were the minor contributors, right? Same rules, different player. Is this still the major contributor? Why? Well, it's getting donated to the same way that guy was. And this is getting donated to the same way that guy is. And this is getting donated to the same way this guy is. But do you want to donate to a negative thing? Do you donate to the rich? No, you don't donate to the rich. So the less you donate, the better. which means that this is your major contributor, and this is your major contributor, and this is your minor. Whereas here, this is your major, this is your minor, and this is your equally minor. Yeah? Cool. I have to think of like, so I'm not using notes, as you can see, so I have to think of situations and like things that I've encountered throughout my studies of orgo that helped me. One of them being this.
I want to see that again. Oh, it flops.
Yeah? Cool.
Okay.
I'm not using notes, as you can see, so I have to think of situations and like things that I've encountered throughout my studies of orgo that helped me. One of them being this.
That ring. The ring.
Yeah. Actually, hold on. I like, is that, you know what I'm getting at, right?
Oh, well, it looks
Yeah,
cute.
and then,
Yeah.
but does it go on these
2F.
two or those two? Because when it comes down, I don't want to like show it, but hold on. You could do it both ways, but it's like one way is just easier, and that's gonna go there. Yeah. Okay. That's what I wanted. Ready? I'm gonna draw this over here. Can I erase this? Okay, cool. You stay there. Because I also want to show you one more thing. And I'm going to show you why carbocation resonance is easier than carbanion resonance. Because the only thing you need to solve a carbanion is one electron push.
Right.
You don't copy this down. By the way, don't copy this one down. This is just for example.
Yeah.
But all you need is one push, and now it's resolved, right?
Mm-hmm. Because it's in the ring and it just keeps going around the ring. And going around the ring has a better distribution.
And then this carbanion can either resonate with the fluorine or it can go through the aromatic ring this way. You guys see how that's going to happen, right? Cool. Let's look at the carbanion, because that's what I actually wanted to look at. So the carbanion, it may be hard to see. This is going to come down this way into the p orbital map that you drew in your head, and you see sp2, 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 right? And that can either break down this way and push the rest of the bonds up, or we can take baby steps. And this is going to resolve to the carbon.
Ah.
And when you're doing resonance, I recommend that you take baby steps. Because if you don't,
You forget.
sometimes you miss stuff.
Yar.
Sometimes you miss stuff, like the fact that this is stabilized by the withdrawing effects of the fluorine. 4.0 electronegativity ain't no joke. And then you go again. And that comes onto this carbon. Always keep track of what carbon you're on. That goes to here. Oop, see, I almost fucked up. And then dude goes there and this guy goes here. And we're just hopping the ring at this point. I'm counting on the Orgo 2 people to tell me if I fuck up. And then this guy goes back. And why are we going back to the beginning? Well, you'll see that we have now inverted the double bonds in the ring, which is very common of benzene. It does this all the time, every single day. That's why it's aromatic. That's what aromaticity is. And if we were to label major and minor contributors, where would they be? That's such a tough question. What would our major contributor be? I'm going to say, hold on, A, B, C, D, and E. There's one major contributor.
Place your bets. Place your bets. I think it's E. I think it has to be E. Just because I feel like the ring would pull the electrons towards, right? I think it has to be E. If it was not for that, then it would have. To be honest, I wouldn't think it would be the rings because, like, the ring itself is already pretty stable, so then it would just be donating. D? You think it's D? Okay, let's find out.
Is it A? Who thinks it's B? Who thinks it's C? Who thinks it's D? And who thinks it's E? You think it's B? A lot of people think it's B. Because it is B.
Ah, shivar!
Because the
No!
fluorine, like I said, pulls away that electron density. It helps to stabilize.
Ah, okay.
But after B, we then need to look at donating effects, withdrawing effects, etc., etc. This gets a little more complicated.
Okay.
But I'll tell you right now, it's probably going to be this guy.
Oh, it's C.
Because the fluorine withdraws from here, which withdraws from there, which withdraws from there, and this fluorine withdraws like that. So you get a little bit of withdrawing rather than being so far away from the fluorines over here. So you can see that negative ions, carbon ions, like to be closer to electronegative
Molecules.
atoms. Correct?
Atom.
Yeah?
Okay.
Very good.
No, it is B. It is B. It's B. It's B.
So that's carbanion
It's B
resonance.
because it's right next to F.
Now,
Like,
spoken
literally
about
right next to
resonance.
an F.
and that can get us to begin to talk. So we talked about, what did we talk about in Gen Chem? Does anyone remember what chapter 2 of Gen Chem was?
Can we see?
Resonance. Ion resonance.
Yeah. Electron, it skips this F. But right here, it is directly on the F. Yeah.
Now, we've spoken about resonance, and that can get us to begin to talk. So we talked about, what did we talk about in Gen Chem? Does anyone remember what chapter 2 of Gen Chem was?
No.
What the name of the chapter was?
No.
Periodic table.
Ah,
And
Shiba.
periodicity. And we had this whole discussion about electronegativity and electron affinity and size and ion size and this and that and blah, 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 and like everything. We talked about everything, right? So we did that. And then we did acids, bases later in that book. And then we did acids, bases last week, or on Tuesday, right? So we did acids, bases. And then we just did resonance. And we talked about the inductive effect and blah, blah, blah. And hybridization, we did our hybridization stuff. We talked about p orbitals, and we did this and that. All of that culminates to one discussion. Base stability. Otherwise known as leaving group stability, because leaving groups are just conjugate bases. Specifically, you can write conjugate base stability, because that's really what it's all about. That's what orgo is all about. These reactions, addition reactions, substitution reactions, TCAIs, carboxylic acid derivatives. It's all about what? My guy nodding his head in the middle, he knows conjugate bases. It's all about conjugate bases. You're an orgo guy, aren't you? So was I. Orgo is a lot of fun if you understand it. There are 5 properties that stabilize a conjugate base. Thank you, Professor Malitsky. I cannot thank him enough. The size of the atom that holds the charge, the electronegativity of the atom that holds the charge, resonance, or lack thereof,
Yeah.
hybridization, or lack thereof, and inductive effects.
I love how his handwriting just trails off.
For all the people back home,
Yeah.
I don't have enough room on this board, and I don't have a wide camera. Go back to my video, the one right before this one, which is chapter 3 and 4, of organic chemistry, and copy down the pKa table that's at the end of that video. For
PKA.
everyone else, I'm putting it on the board here. Okay? HF, H3O plus. What was after H3O? No, sorry.
We can
I'm
go back
forgetting.
later.
H3O plus, HF, H2CO3, HSR, NH4. Hold on. I don't know if I gave you this one last time. HCN, is that on yours? Yeah? HCN. And then we have H2O, and then ROH, and then SH3. It goes up, the stability of the up here by H, correct? And when we talk about the pK, so let's do some comparisons. Oh, I know what's missing from this table, and it's a really big one. Carbon 3 to
Come back to me, bro.
So let's say that we have a reaction
Yeah.
between this and this. What's going to protonate what?
It's gonna protonate what?
What's the stronger acid based on the table? Just based on the table.
It's OH.
Yeah, so we're going to get
OH is gonna take, right? Yeah, yeah.
that. That's what we're going to get if they reacted. But classically, you won't be shown it like this. You're going to be shown it like this. Oops. Why did I look back over there? You're going to be shown it like this. And you're going to be asked,
Delta G FWD.
delta G of the forward reaction. And your 3 choices, 4 choices. Less than 0, greater than 0, equal to 0, cannot determine with the given information.
Greater.
I'll give you a hint. It's not D.
Greater than.
Oh, Professor Malitsky used to do that. Dude, I'm just turning into him. Whenever he used to cross stuff across the board, he'd go like this and just like walk by the board like that. If you guys can't tell, I have a lot of love for him. Okay, so before we answer, let's talk about the thermodynamics of this process. What are we talking about? We're talking about conjugate base stability. Here is an acid, and I'm going to start using the other colors now.
Yay.
because we need to display two different reactions. Here's an acid and its conjugate base.
Base.
And here is another acid in a different reaction, and here is its conjugate base. And we have to ask ourselves, which of the conjugate bases is more conjugate base, is cooler, is more fetch? So which one's more stable, right? Sulfur. And a lot of people will say this, I don't know what to call this. It's a thiolate, right? But this thiolate is more stable than that ethoxide, right?
Yeah.
Because of the fact that HSR has a pK of 8 and ROH has a pK of 16, 18. But what does that mean? Like, why? Why is it more stable? Well, let's take a look at the 5 things that stabilize a conjugate base. What does this have going for it that this doesn't? Huh? It's bigger. It's bigger. But the electronegativity here is greater. And there's no inductive effects on either side. And the hybridization is the same. And there's no resonance. But remember what I said way back in the Gen Chem chapter, chapter 2. If you have to rewatch that video, I would. It's essential to your understanding of conjugate bases. Do you remember what I said? That electrons, they're like tiny little infants. They're like these, what time is it?
7:20.
Beautiful. They're like these little kids, right? They want to run around and scramble and do whatever the fuck they want to do. So if you confine them to a space this big, or if you give them this big of a playground, what are they going to prefer? They're going to prefer that. So size is more important there, and the conjugate base there is more stable. Yeah? Because this is a 3p element, and this is a 2p element. So that's size out of the way.
Size wins.
So the delta G of the forward reaction is what? Negative or positive? Negative.
Oh,
Very
negative.
good.
Oh, negative is more favorable.
Size.
Minus this GL is
Over
really
two people
free
should be
energy.
screaming.
Oh, okay, okay.
Screaming. Which way does it go? Left or right?
Left.
Come on, guys. Or go 2 people. We just talked about how ridiculously strong that is. It's going to be this guy.
Yes!
what? What's bigger? What's bigger? B, C, N, O, F. As we go down a period, we decrease in size. So nitrogen is actually slightly larger, but slightly. So it's not that much more room. We're not talking about difference between periods. So size matters between periods, but electronegativity matters within a period or between groups.
Yay.
So group 16 versus 15, the electronegativity is what matters. And that's why this is more stable. And the delta G of the forward reaction would be positive. That's how it's going to be presented to you on the MCAT. Delta G of the forward reaction. Ba, 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 ba.
Ba, 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 ba.
Now on to why we talked about resonance in the first place.
Oh shit. Oh god. Okay.
Oxygen, same electronegativity, same size. However, what does this have going for it?
Resonance?
Resonance. Very good.
Oh.
It splits up its negative charge amongst 2 species on the same molecule.
Yes, yes.
And that, what does that contribute? It goes from 16 to 18 to 4. How much of a drop is that? A lot of people say, what? Let's say it's 16 minus 4, that's 12. They're like, oh, 12x. No. pH scales and pKa scales are logarithmic. That is a 10 to the 12th stability. Meaning that this guy is how many times more acidic than ethanol? Ethanoic acid is how many times more acidic than ethanol? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That many times more acidic than ethanol. Which is why if you drink vinegar, it'll taste acidic, but if you drink ethanol, you might crash your car. But what does your body do with ethanol? Do you guys know? Turns it into acetic acid. Your body takes ethanol, and this is why we do redox reactions, because I'll teach you guys this in biochem. It takes ethanol, and it turns it into acetaldehyde, and then it turns that acetaldehyde into ethanoic acid. Oxidation, oxidation. And do you guys know Asian glow? How when people of Eastern Asian descent drink, they turn red in the face? It's because they lack this enzyme. And acetaldehyde is really toxic to your body, so it causes them to get flushed because of the cytokine release. This is inflammatory. This is what gives you a hangover.
Can you?
So if you drink a lot of water and you dilute this and you
You know
piss it out
what,
of your
OTR,
system
you're
the
not
night
even
before you
listening,
wake up,
bro.
you won't get a hangover.
You're freaking doing physics!
I don't know.
으르세!
Maybe you should find out.
바카야로가!
But mind you, if you build up more of that enzyme, you're drunk.
Throw back
for
to the
less time.
previous video? Yeah! You should have been taking notes on this. You don't need to see this again.
Pretty much.
So freaking cool. Everything's
Right,
coming
James,
full
we're good?
circle, man.
Yeah? Cool. Hybridization is very, very, very simply shown in two of those things. Or just, you'll see it like this.
Are you taking notes? Kind of, yeah. I don't know if you heard my pen clicking. Sometimes it went
What's more stable? What's the more stable conjugate base?
Ooh.
Well, we've got this guy at what? A 25, and this guy at a 40, right? And we always go towards the conjugate base of the more strong acid. So why is this guy more stable than this guy? Let's take a look.
Wasn't it?
Versus this is sp hybridized, right? Remember my trick. Whatever you're not using, what is that? Free p orbitals. P orbital, p orbital. Those are both contributing to the 2 pi bonds with the adjacent carbon, right? But what else are they doing? P orbitals are louder. Electronegative. Every time I say it, p orbitals are
Electronegative.
electronegative.
Yeah.
They are literally pulling those electrons closer to the structure, stopping them from interacting with their surroundings. And when the electrons interact with their surroundings less, you stabilize the conjugate base. You have 2 p orbitals there. How many do you have here? One,
One.
because that's sp2. And if you look, if you're not using it, it's free. It's only 1. That's 2. There you go. Conjugate base stabilization by hybridization. And lastly, everyone's favorite, and the MCAT's favorite, because you're going to get a question like this, inductive effects.
どうしようかな?
The question looks like this. Which of the following is the strongest acid?
Wrong.
This guy, right? Why? Well, let's deprotonate all of these and look at the conjugate bases.
Ah, おやすみなさい. Good night, OTR. You have work? Good
Same
job
thing,
studying
right?
today.
Get used to seeing them in different
お疲れ.
configurations. They're not always going to show it to you upright.
おやすみ. おやすみ.
This guy, all of them have resonance going for them. The size is the same. The hybridization is the same. The electronegativity is the same. Everything else is the same. Now we got to look at inductive effects. This guy, the R group is donating into the carboxylate. Why am I saying the carboxylate? Because it's resonating. That's the whole electron density right there. Here you got the donating, but you also have the F really withdrawing here. Right? And over here, you got donation, and you got a little bit of withdrawal, but it's like 3 steps away, right? So the most withdrawal is going to happen over here, and that's why this guy's the strongest acid. Does that make sense to even the people taking Orgo 1?
Likewise,
Very
good
good.
night. Good
Good,
night.
good, good.
Sleep
I
well,
may
Max.
forget what you guys
Oyasumi.
do for
Oyasumi. Oyasumi.
It's been
Have a
4
good day at
years.
work tomorrow.
It's been a good 4 years. 3.5. I'm not that old. Oh god, I was 19 when I took Orgo. You guys know how old I am now? 23. So those are the 5 factors that stabilize conjugate bases. And now you'll be able to tell, right, on the MCAT, when someone says which of these... I don't want to do chirality right now.
I know.
When
He's
someone says which
well.
of
When
these
he made
happen
this, was
faster,
he's about like 25
right?
now. He's about
when someone says which of
25
those
right now, I
reactions-
think.
Like which of those leaving groups
Yeah.
leaves faster.
You
you'll
baby
be able to
here
tell.
though. He's so
Because when this
baby.
leaves, it's going to make BR minus.
Baby,
And when this leaves, it's
baby
going to make
man.
I minus. And even without the pKa table, BR and I, F, Cl, BR, I, going down the row, the size increases. And if iodine is larger than BR, it's more stable, and that's going to leave faster. That's it. Guys, I really wish I could go through the whole carboxylic acid derivative thing with you. This took a little longer than expected, and I have to go study for my exam. It's on Monday. So we'll do that next time. I'm not going to be here on Tuesday. I'll see you on Thursday. So on Thursday, we'll have a full lecture, 6 to 9 p.m. like we did before. We'll go over the carboxylic acid derivative stuff, and we'll circle back on chapters
I
1
think
and 2
he's
of
in
organic
med
chemistry and
school.
reading and
Yeah.
stuff. But before
So
you
like
leave,
he teaches this class
before you
from
leave,
6 to 8 p.m. and then he studies
Radical
for
resonance.
8 to 12 a.m. That's his schedule.
Have you guys
yeah.
ever heard of
And then he
antioxidants?
studies before this class, I think.
I'm chock full of them because I'm brown. I'm eating ginger and turmeric and garlic all over the place. I'm chock full of antioxidants, right? Antioxidants. What are oxidants? They're things in your body that can oxidize, right? And the biggest ones are ones that...
Antioxidants give you melanin or something like that. He's saying that's the reason why he's brown. Because he eats so much turmeric and other stuff like that.
we're able to get from oxygen. And oxygen in our body can turn into a plethora of things. One of the most important ones being a reactive oxygen species. We talked about this back in bio, chapter 1. The cell peroxisomes, right? Make what? They make hydroxide radical. And in your body, you need a way to stabilize that so that it doesn't go around and bend your fucking DNA over and give you cancer.
Yeah.
You need a way to do that. Why should you guys not suntan? I don't care how pale you are.
Oh,
It's because you're making that in your body using the light.
not
Quite
good.
literally giving yourself cancer.
I thought they get brown when they
Don't
I
tan.
mean, that's one thing too, yeah.
I
But then
have
it could
melanin.
also...
I do not tan.
Some people
I
have
this color
natural.
all year round.
Natural, but then other people don't
So,
get natural. That's like the
One
Kim
antioxidant
K
in your
skin
body
tan.
is what? Tyrosine. What is tyrosine? It's an amino acid whose structure looks like this. It is phenylalanine with an OH group. So it is a phenol on top of alanine. Right? Not phenyl on top of alanine, because phenyl means benzene ring, but a phenol on top of alanine. Specifically a paraphenol. Right? Orthometapara. And when a hydroxide radical comes into contact with tyrosine, tyrosine is able to couple the radical. A 1 electron donation from the proton and a 1 electron donation this way. Those are called fish hook arrows. 1 electron. Double-headed arrows are 2 electrons. Okay? That's going to create H2O from the hydroxide radical, which is now stable as water, and we're going to create a tyrosine radical.
Tyrosine radical.
Always draw your radical electron a little bigger, so that no
PHENOL.
one mistakes it.
And then fent is fentanyl
Guys
with an
ready to see
A,
the magic?
not an O.
This guy's ready. Fish hook arrow down, fish hook arrow in, fish hook arrow out. That is radical resonance, where the radical disperses itself throughout the benzene ring. And I'm going to take this, and I'm going to say R, okay? Because I'm not going to keep drawing it. So when it disperses itself throughout the benzene ring, you get R, and then you get double bond
Guess
to
you
the
stay
O 'cause
poured
you
in.
made it
I'm
with
not
that
gonna start
one
a
radical
juggling, man.
electron. The radical goes here, and we go here
Honest
and
worker.
here. This comes down, down, and in. More resonance. R. Double bond O. Orgo 2 people. If this was not a radical, what would this structure be called? It's called a quinone.
Yes.
Down, down, and in. More resonance. R. And yes, I know I'm changing the orientation of the molecule a lot. That is on purpose. And then up, down, and in. And we come all the way back to the oxygen. And we have flipped the orientation of the double bonds. That is how tyrosine stabilizes the radical. It spins it around and around and around and around and around the benzene ring until tyrosine radical couples with another tyrosine radical and makes
2 tyrosine? 2 tyrosines bonded to each other? Is that it?
so the radical here couples with
Another radical. I think it's so cool how he remembers all the structures. That's really hard, I feel like. Oh.
look, everyone look. Everyone
I'm looking.
couple and you make a dityrosine compound which can be urinated out of the body.
Wow. So that's how you
We started with a hydroxide radical or 2, and we had 2
Detoxify your
tyrosines
body.
which captured them, stabilized them inside of their resonance, coupled to one another, and will subsequently be urinated out of the body. Or we will learn in biochem that glutathione, which is a radical scavenger, will come reduce this, become oxidized. Oxidized glutathione forms a cysteine bridge, a disulfide bond, which will get reduced by NADPH, and it cycles. We will learn about glutathione and radical scavenging in ways other than this when we talk about biochemistry. But if you have taken biochemistry, you have an interest in biochemistry, glutathione is a protein which has a cysteine residue inside of it. And that cysteine residue sees this radical, right? Reduces it with one of its own electrons, forms a cysteine radical, couples with another cysteine radical from another glutathione, and forms a disulfide bridge between the 2 glutathiones. That disulfide bridge can be reduced by NADPH, forming NADP+, which cycles back into the pentose phosphate pathway and regenerates NADPH. If you followed that, you're quite good at biochemistry. Isn't it?
Gary.
All right, and if you followed that back home, congratulations. And if you followed all of this back home, congratulations. This was one of the tougher lectures that I've given, but I hope that it gave you a little bit more of a background of how base stability and resonance works before we move forward in organic chemistry. Because this will be very important when we do the Aldol, Claisen, Michael, and Dieckmann condensations. Understood?
Yeah.
Have a great night. I'll see you guys next time. Please go home.
Yay! That was
We are.
the scariest lecture, I think. Did you follow all of that? Yeah, that was fun. That was very fun. But I will say, I think, you know what? For today, we got through 3 of them. Very impressive, I would say. We got through 3. And I have 3 more left. So, that's pretty awesome. The rest are gonna add up to about an hour and 30 minutes left. So, we can split up for the night. Great job! My back is killing me. My back is literally killing me. Oh, thank you so much. Thank you, thank you. Thank you for watching me study. Whoa, why's my VTube still tweaking out? Yeah, we're stopping here for today. Ah! I think maybe my phone's too hot. Whoa! 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 Okay, I think it's okay now. Oh yeah, Subi, you guys, good morning. If it's morning for you guys, thank you. Thank you for studying with me and enriching your brain. I will see you. Tomorrow? Question mark? Tomorrow. Yeah. Oh yeah, Subi. Bye bye. Ochu ucha. Yay.